I guess just to complete the story too, that two other green functions which we have never mentioned, but are sort of the, well, maybe it's just one here, that the theory is developed in terms of, like if you read Federer and Lec or something, it's a time-ordered green function. So superscript I, meaning it's time-ordered. And this is relevant when you start doing perturbation theory. So there's a time ordering operator there. This is sort of the fundamental green function that you need when you start doing perturbation theory, and all the others sort of evolve out of this thing. So what the time ordering operator does, it means that later times are on the left, which means as you know, t and t prime are two independent variables in general, and so say hold t prime fixed and vary t. If t is, as t, you know, becomes greater than or less than t prime, you switch the order of these operators. And so we could write that out specifically as gt ij tt prime is equal to theta t minus t prime. That's a capital T, yeah. It's a time ordering operator. So it means that, well, this is explicitly what I'm writing. Let me write it in terms of the C's and C daggers. I'll explicitly write out what that expression means and then go back and talk about it. So I guess each one has a minus I over H bar. And then, so if t is greater than t prime, then I have Ci of t, Cj dagger of t prime. And if t is less than t prime, then I have the opposite. And whenever I flip the operators, I introduce a negative sign. So this becomes a plus I over H bar. And I just switch the order of the operators. C, J, dagger of T prime, Ci of T. So that's explicitly what that expression means up top and what the time ordering operator does. So if T is greater than T prime, I just have Ci, Cj dagger, Tt prime. And if T is less than T prime, then I flip the operators. And whenever I flip them, I have to introduce a negative sign because of the, well, we just do. It's not really equal time, but in general, when we flip the ordering, we introduce a negative sign. And so, you know, there's a lot of, this is related to all the other operators. So for example, this equals gt tt prime is equal to theta t minus t prime g greater than tt prime plus theta t prime minus t g less than t prime. And now, you know, you can see why, you know, instead of using gn and gp, when you start really manipulating these, it's easier to work with g less than and g greater than. I don't have to introduce factors of I to go back and forth between the other various definitions of the green functions. And it's also, just using shorthand notation, gt is also equal to the retarded green function plus g greater than. Right? Because the retarded one only exists for theta t minus t prime, when t is greater than t prime. So all these different green functions and correlation functions, if you go back and look at the definitions, they're all closely interrelated. Okay, so now that we've defined them all in this representation, you know, we have previously talked about equations of motion that our green functions have to obey, for example. So we'll start talking about the equations of motion. So specifically, before we had E minus H, and I'm not going to worry about the sigmas for now. E minus H acting on my retarded Green function gave me the identity. For example, that's one of my equations of motion. And if we don't have any self-energies, then we also had that E minus H acting on G less than is 0. It's just a correlation function. And so we're going to go now rederive these equations of motion using these definitions of the Green function and show that they still hold. And the way we have to do that is start in the time domain, and we'll get the equivalent of these relationships in the time domain, and then you just Fourier transform them to energy, and you get what we had previously. So let's start with G less than. So I have IH bar ddt G less than IJ TT prime. And well, ddt is only going to act on the variable t, so I can move that through the t prime. T prime is just unaffected by ddt. And so I'm looking at an IH bar ddt Ci of t is just Ci comma h. And so let's take a just generic single particle Hamiltonian. H is equal to sum Mn H Mn Cm dagger Cn. So there's a generic single particle Hamiltonian. And now we have to evaluate the commutator of that with our Ci, right? So Ci comma h is equal to sum Mn H Mn Ci Cm dagger Cn minus Cm dagger Cn Ci. So we get to evaluate that thing in the brackets. And the way you always have to do it is just push, start with one term or the other, choose a term arbitrarily, and push the Ci all the way through until it matches the other term, and hope something's going to cancel and work out nice for you. So we'll start with the term on the left. We'll start with this guy here and show, some relation to the other term. So we have to start pushing that Ci through to the other side. And the way we do that is use our anticommutation relationships. So Ci Cm dagger is equal to Cm dagger Ci, I'm sorry. Yeah, I can write it like that. It's equal to negative Cm dagger Ci plus delta I comma m. I mean, that's my anti-commutation relationship. Ci Cm dagger plus Cm dagger Ci is delta I m, right? So I replace that, put this into the term above, and so the term above becomes, I'll just rewrite it, Ci Cm dagger Cn is equal to delta I comma m Cn minus Cm dagger Ci Cn. And so I got to do push this. I got to do this one more time. Push the Ci through. I got to bring it over here to make it look like that other term. And so, well, again, I know that Ci Cn plus Cn Ci is 0, right? So this is just equal to negative Cn Ci. Right, just flipping them. because CI-CN plus CN-CI equals 0. Right, the anti-commutation relation, the only thing that equals something is when one is a dagger and the other isn't. But if they're both not daggered, or if they're both daggered, the anti-commutation relationship is 0. So I can make that, so this term just becomes plus CM dagger CN CI, and that cancels that other term up there. So this term cancels this term, and the only thing I'm left with is this term. And so I get that CI comma H is equal to some N H I comma N C N. So if I put that back into, where did we start? It goes back into here. So at this point I have IH bar DDT G less than IJ TT prime is equal to I over H bar I over H bar CJ dagger T prime CI comma H, and this was equal to, that's equal to some N H I comma N I over H bar C J dagger of T prime Cn of T, and that's equal to some N HIN G less than N comma J TT prime. So the equation of motion we have is that IH bar DDT G less than TT prime is equal to H G less than TT prime. And if we Fourier transform that into energy, the IH bar DDT just becomes energy, and we have E minus H G less than equals 0 in terms of energy.
H commute with C. That's it.
Where are you asking?
With the first line, H was in the middle.
In the first, like up here?
Yeah, for the first line. CJ dagger.
This guy?
There was an H.
Or back? I mean, back before, or
No, for the first line.
This guy
Yes.
here?
Here.
Okay.
The first line, CJ dagger. Then there was an H. Then CN. HS came.
I just don't see. And here's the first line. What H are you talking about?
HJN. First one.
I mean, H is all on the left. What are you asking?
We replaced CIH, the compression.
Here, this.
Yes. And it was on the right side.
We replaced it with this.
So HIN was on the right side of CJ dagger.
Let me just back up and see something. Right. Okay. So this is the operator. These are just matrix elements. These are numbers.
Okay.
Right? Because H is this whole. This is H. Here's H. The whole thing. Okay. The matrix elements are just numbers. So, yeah. So this is, as before we introduce any self-energies, this is exactly what we had before for G less than. Now we're going to use this to derive the equation of motion for the retarded green function, which is what we're really after, because that's sort of the fundamental equation that we work with all the time to get everything else. So let's go back and look at, just write down the definition of our retarded green function. So GR IJ TT prime is equal to theta T minus T prime minus I over H bar, and then your operator CIT CJ dagger T prime plus CJ dagger T prime CI of T. That was our retarded green function. And we've already just worked through what, IH bar DDT does acting on CI of T. We just did that problem, right? If we now hit this with IH bar DDT, we already know what it does to the operators. It only acts on CI of T, and we know exactly what it does. It does, we end up with that. So the only new thing in there is the theta function. And so IH bar DDT acting on the green function, IH bar DDT acting on my retarded green function. Well, first it's going to hit the theta function. When it hits the theta function, I'm going to get a delta T minus T prime when it hits the theta function. Maybe let me copy and paste that definition so we can see what we're looking at. Okay, so IH bar DDT, the first thing it hits is the theta function. It gives me a delta function, and the IH bar kills off the negative I over H bar, right? And since I have a delta T minus T prime, I can go ahead and evaluate my C operators when T equals T prime. And what does that give me?
Anticommutation.
It's the anticommutation, and so it's what?
0.
It's what?
0.
What's the anticommutation relationship of CI and CJ dagger?
Oh, delta IJ.
And delta IJ. So delta T minus T prime, delta I comma J. That's the first term I get just from hitting the theta function. And then, just like, when it hits the operators, the term I'm going to get from the operators is going to look just like what I got from hitting G less than, because it's only acting on CI of T, which is all it was acting on with G less than also. So I'm going to get the exact same form, except I just replace G less than with GR. Right, this is exactly what I had for G less than. I had, H times G less than, matrix multiplication. So when it acts on the C operators, I get the exact same form for GR. So I get two terms now. And so if I Fourier transform, the IH bar DDT just becomes energy, and I get E minus H acting on GR of E is my identity delta IJ. Because I Fourier transform the delta function, it just becomes 1 in terms of going from time to energy. And I'm just left with the delta IJ. So the equations of motion for these things satisfy exactly what we had before, where in terms of when I Fourier transform this just becomes energy. there's nothing, this is the same matrix we had before. This matrix is exactly the matrix we had before. It is the matrix elements of the Hamiltonian in our localized orbital representation. So after all this fancy second quantization, we're back to exactly the same equations we had starting from wave functions, which is necessarily so, otherwise you'd be solving some different equation. It's got to be the same equations for the same system. So this is the same matrix you've been looking at from the beginning of the course, your Hamiltonian matrix element. So all we've done is shown all that fancy notation gives you the same equations we're already familiar with. It will give you something more when you start doing inelastic scattering and perturbation theory. That's when its power really comes into play. But so far, for just ballistic transport, what can I really do in 45 minutes? I don't think I can do perturbation theory, but what I can do is current. So how you derive, say, traditionally the current operator. Let's just look at how people derive the current operator in the second quantized representation. Okay, current. Right, so far we just have our green functions, but we don't know anything. We do have to have. We know the equation. When it comes down to solving them, the equations are exactly the same for Gn, which will give you the electron density, and we could do just proceed as normal. But it would be nice to understand how some of this is derived in this representation. So let's look at current. So the way current is really always derived is through a continuity relationship. So it's derived by considering dn dt, some change in electron density with time. So let n be the total number of electrons in the device. So now we want to calculate. And the way people do this, starting from the green function, is they say that's minus I h bar limit, because you can't just set these equal to right away. T prime goes to T. T prime goes to T. Of ddt plus ddt prime g less than of t comma t prime. So the way this is evaluated is you look at the equation of motion for g less than, and I'm going to have to jump ahead since we haven't had time to derive the self-energies in this expression, so I'll just write it down. So IH bar ddt of g less than tt prime minus h0 g less than of tt prime is equal to, and this is where I'm just going to have to throw in the self-energies without having really derived them in this representation. So the form of the self-energies expression in the time domain is like this. Integral of dt1 sigma r due to my boundaries, these boundary self-energies that we've been dealing with from the beginning, t comma t1. And if we had some kind of self-energy due to phonons, that would be thrown in here also, sigma r. I'll put p for phonons, t comma t1, acting on G less than of T1 comma T prime. So these retarded self-energies we normally put on the left-hand side of the equation. Right, we had like E minus H minus sigma R acting on G less than was sigma less than GA is the expression we had derived. But I'm putting all the self-energies on the right-hand side. So I've also got this other term plus sigma less than, again due to the boundaries, T comma T1, plus sigma less than due to the phonons, T comma T1, acting on GA of T1 comma T prime. And when we worked in energy, these were just a product. We had sigma times G less than. But when you Fourier transform, if you have a product in one domain, it's convolution in the other, right? So here we see it's a convolution in the time domain. I mean, we'd still have a product in terms of H0, but H0 is time independent. So H0 is like delta T minus T prime. It's instantaneous. And so we have that, and we can also write an equation for IH bar d dt prime, the time derivative acting on the t prime coordinate. And so that's minus IH bar d dt prime G less than of T comma T prime minus G less than TT prime H0 is sort of like we're taking the what do you call it, the Hermitian conjugate of the whole equation. And that's going to equal, okay, so those are the two equations that we need to evaluate this expression up here. This guy. Because we had to do a DDT, a DDT prime, and add them together. Take the limit as t prime goes to t. Is the way that works. So let's see, what is it we got to evaluate? We got to evaluate minus IH bar, this DDT plus DDT prime, right? Minus IH bar DDT plus DDT prime. And so, here's IH bar DDT in this line right below it, plus IH bar DDT. This is minus IH bar DDT prime. I need to add the two together, so by adding the two together, I'm going to subtract these two expressions. Okay, to add these two together, I have to subtract these two expressions because one has a plus IH bar DDT, the other is minus IH bar DDT prime. And so I've got that d end of my device dt dt1, and I'm going to suppress all the time coordinates, so this convolution integral is being applied. So I have g less than, okay, phew. So, and this has got to be equal to IH bar dn dt. In steady state has got to be equal to 0. So in steady state, this term's 0, right? G less than and equal time is just your electron density at a given site. And so that's going to commute with H0. This term is 0. G less than and equal time is just your electron density. So now for the moment, let's just ignore the phonons and look at the boundary terms. So we have the boundary terms in that integral. So these were our boundary self-energies as before. We have G less than sigma A plus GR sigma less than minus sigma R G less than minus sigma less than GA. And so now we're going to break these boundary self-energies up into, they have a left and a right component, right? We're assuming two contacts. So we're going to break them up into a left and a right component. And we know that whatever must be flowing into one contact is flowing out of the other because there's no net change in steady state in the electron density in the device. And so each term individually has got to give you the current with just a change of sign. So let's just look at, say, the left contact. And so the current flowing out of the left contact into the device, from the left contact into the device, would be J is equal, now putting, going from time back into energy, dE over 2 pi h bar times, and now everything's just a function of energy. G less than sigma A, so I'll just left, plus GR sigma less than left minus sigma R left G less than minus sigma less than left GA. So those are the four terms, again, where I'm just looking only at the left contact ones from a given contact. And each term is just a function of energy. So I can combine something here. What can I combine? Sigma, what did I do? Sigma less than G less than GR, sigma less than sigma G less sigma less than GA. Sigma less. So I guess one thing yeah.
G less than was a function of time. Now it's a function of energy. So was there any Fourier transform?
Yeah, this is so here, this is, if you look at this expression, this is like, T1, T1, T prime, or yeah, T1, T1, T prime. For any one of these, this is convolution. In the time domain, this is convolution. And of course, when you Fourier transform a convolution, you get a product in the energy domain. So that's, I got to move fast or short. So that's, when you go back and forth, in one domain it's got to be convolution, the other is going to be a product. I guess the other thing is that when I calculate current, finally I'm going to trace, there's sort of an implied trace here. I trace over all the states to get the total current. And by putting in the trace there, it means I can rotate the order of the operators. Right? Matrices under a trace can be, what do you call it, cyclically permuted under the trace. And so that means I can combine some. I'll look at the 2 with a sigma less than, and I get a sigma less than times a GR minus GA minus a G less than times a sigma R minus sigma A. Just factoring them out and flipping the order as necessary. And this is just minus I times the spectral function. This is just minus I times gamma L. And this is just I F left times gamma L. And so putting all that together, we have that J is equal to the integral dE over 2 pi h bar trace of gamma L F left A. And when we derived this in class, we weren't using G less than, we were using Gn. So let's see, there's a difference in a factor of I here. So I times G less than just gives me a minus Gn. Because G less than is defined as a factor of I with an extra factor of I. So this is what we derived. This was our numerically efficient expression for the current that we derived in class. Or because gamma L only couples to, like, you know, the 1,1 element A11 and Gn11. What else? Also, this is kind of working backwards. J. So I guess I'm going to write this down and show that the two are equivalent. J is equal to integral dE over 2 pi h bar trace T01 G less than 10 minus T10 G less than 0,1. So these are the G less thans that actually, so our devices as usual starts at 1, and so 0 would be in the left contact. And so we go back and okay, so what oh shoot. To derive this, I need a Dyson equation you haven't seen yet because we had to skip all the perturbation part. And so this won't make a lot of sense. I'm just going to write down this Dyson equation and say that it takes about another lecture and a half to derive this. But the Dyson equations for these correlation functions look a little different than the ones you've seen. So this is the ones for the retarded green functions are just exactly like what you've been dealing with, but the ones for the correlation functions are a little strange looking because they mix up all the, and to derive that you really have to spend at least another lecture. So this is what the Dyson equations look like for these guys. So I've got one for g less than 0, 1, one for g less than 1, 0, 1, 1, t, and I'm using like the alternate form of Dyson equation for this guy. So I mean, the big G's and the little G's all have the same meaning they did before. The little G's are for the system that's disconnected between 0 and 1. The big G's are the exact green functions of the full system. And so, I only have full G's for the 1, 1, which is in the device, which is what I need. Because that's what we finally calculate, the exact G's of the device. We never calculate the exact G of the lead. And so these G00 terms are just my surface green function of the left lead. Yeah? Just the exact green function of the left lead without any connection. So I have my surface green function, and I have my exact G11 green functions. And so I put those terms back up into the expression above, and what do I get? What do I get? I get, well, I guess we can just put it, so I'll just worry about the curly brackets. So I've got curly bracket T01, G00, T, let's see, T01 I want, oh, wrong one, sorry. So T01, and then G less than 1, 0, so the exact G11, T10, G less than 0, 0, plus T01, G less than 1, 1. I guess I got to keep track of all my, because I got different kind of green functions. T10, GA00, 0, minus T10, now I need G less than 0, 1, GR00, T01, G less than 1, 1, plus, or minus, sorry, minus T10, G less than 0, 0, T01, GA11. Okay, and I didn't write out all this algebra in the notes, so let's just see what happens if this really works out. So what happens here? So this is all under the trace, so I can cyclically permute all this stuff. So, and I want to get it to look like this expression here, or maybe to get it back into this form here. So let's see, what can I sort of immediately recognize? So this, I'll just pull out terms that are obvious. Right, that's sigma r due to the left boundary. What else have I got? This is sigma less than due to that boundary, left boundary. And if I cyclically permute under the trace, and I can move this, move this term over to here, and then this just becomes sigma A due to the boundary. And playing the same trick here, moving this term over there, then This stuff just gives me a sigma less than due to the boundary. And now I gotta combine all that stuff, bring it all together. And so, let's see if I try to collect all this stuff, what am I gonna have? I'm gonna have GR sigma less than plus G less than sigma A minus sigma R G less than minus sigma less than GA. Again, it's all under the trace. I can cyclically permute as needed. So it's exactly what we had before. I've got my, sigma less than times GR minus GA. And I've got a, what else? A G less than times, or say minus G less than sigma R minus sigma A minus sigma less than times sigma R minus sigma A. And if you look at these are the two terms we had before when we, right here, sigma less than GR minus GA minus sigma less than sigma R minus sigma A up here. So, and this is what became this. So we're basically done. We showed that these two expressions for the current, the one that we've derived earlier, and this one, are equivalent. And in general, there's nothing special about the sites 1 and 0. So in general, if you have this tight binding chain model, we've never really talked about a current operator for any position in the device. But in general, the current flowing between any two nodes in your device is just integral dE over 2 pi h bar trace T n comma n plus 1 G less than n plus 1 comma n minus T n plus 1 comma n G less than n comma n plus 1. And you can replace these G less n's with your G sub n's, and you'll introduce just the extra factor of I, because that's how they're related. We were working with Gn before. With G less than, they're just related by a factor of I. So you'd have an I out front. And so this is the current that's flowing between nodes n and n plus 1 in your, say, linear chain model. Or if these represent layers, block layers, and it'd be the total current flowing between block n and n plus 1. And for ballistic transport, we haven't needed to worry about this because current is conserved. It's the same current flowing everywhere. But once you turn on, say, phonon scattering, then if you look at this at energy by energy, if you integrate over all energies, you still have conservation of current, but you will see it flowing at different energies in different regions of your device as the current, as the electrons emit phonons as they cross the device. All right, so we've rederived our current expressions. By default, we already had the same electron density expressions just by looking at the definition of G less than or G sub n, Gn in this second quantized notation. The only thing, if you look back, we had a bunch of other self-energies somewhere. These guys for the phonons. Right, we had all these phonon self-energies in this expression. These guys, these guys. So the question is, what about those guys? Well, it turns out if you put in expressions, actual expressions for the phonon self-energies, you're going to find that the integral transform to energy. The integral over energy of those four terms always gives you 0, so there's no contribution to the current from the phonon scattering self-energies. This will locally give you 0. And so this is one thing that, when you derive self-energies for various scattering mechanisms, that you always check. No matter what scattering mechanism you're working with, you're going to have these 4 terms, and you're going to have showing up in this is like the divergence of the current. And the first thing you check is that they give you 0, that they're not causing current to either decay or grow. And you call that a current conserving expression for the self-energy. And so I guess that's about all the time we have for this quarter. There's really nothing else I can cover in this time. So there's homework due Friday. If you have any questions, don't hesitate to ask. There weren't a lot of questions at the last discussion section, which I sort of took as an indication that people really hadn't started looking at it very much yet. But if you have questions, don't hesitate to ask. It's your last homework. As far as I can tell, I don't know what I could... Yeah, we'll call that the last homework. We're done. We're done. What? No, just the one, this number, homework 3, will be due next Friday. That's it. I was thinking, I could have you do some commutation stuff, but that's just, you haven't, I kind of rushed through it really fast. We haven't had time to any of that sink in, so we're good. This is just next Friday. We can email it to me, or I can be here for one last frantic discussion if you want. Just let me know. You can email me or whatever. All right, I guess that's good. So we'll call that a wrap. Thank you very much.